Hello all, welcome back to EduMoon tutorials. In this video, we'll be discussing our next topic, that is Turing machine. So this is the machine which is powerful from compared to all the other machines. So this will be accepting the type 0 languages. So let us see the structure of the machine first of all. So this contains a tape, an input tape, and a finite control. So here we can see an infinite tape which is containing the input symbols and a read-write head and a finite control. So this read-write head is going to read the symbols on the tape. So let us see the tuples of this machine. So this has the same tuples like a finite automata like Q, sigma, delta, Q naught and F. And additionally we have two more here. So which are called as tape symbols, which is denoted by capital gamma here. So you can see the capital gamma and a blank space B. So these are the seven tuples of a Turing machine, where Q is the set of states. We already know that the set of states, and sigma is the input symbols, and delta is a transition function. We will see that here. And Q naught is initial state. So this is the initial state. And F is the set of final states. And where comes to this one, capital gamma is nothing but the tape symbols. So which are used for reading and writing on the tape. You can also write it on the tape because this is the read head, we already seen that. So this is the read head we have. And B is the blank space. So this blank space is used to indicate the end of the string, because here we have the tape as infinite tape. For example, the string is processed in this tape like this one. So at the end of the input symbol or as input string, will try to place a blank space B. And in some textbooks we have that instead of this B we will be having the other notations like a dollar or a delta. So no matter, the meaning is same, which is indicating the end of the string here. So coming to the important one, that is the delta transition. So delta transition here is, first of all, this tape symbols also contains the input symbols, and also the blank space are also the subset of the tape symbols. So likewise you can write it as the sigma is a subset of tape symbol, as well as the blank space is also a subset of the tape symbols. Coming to the delta transition, finally the delta transition will be like Q cross tape symbol. So tape symbol is, you can see that it can either read the input symbol or the tape symbol or the blank space, and it goes to the next state. Does some operation, either a read operation or a write operation on the tape, and then it goes in the right side or left side. So here the control can move either right side or left side. This is the finite control which can move, the read write head can move both right hand side or the left hand side. So that is the important transition function of the Turing machine here. So let us take an example of a language L equal to 0 power n 1 power n, so where n is greater than 0. So we already discussed this type of problem for the automata. So let us solve this problem using the Turing machine. So this language L equal to 0 power n and 1 power n, where n greater than or equal to 0, generate the strings like 01, 0011, 00011, and so on. So we have done the similar problem for the push down automata, where we pushed the zeros into the stack and we just popped out them once the ones occurred. So when the equal number of zeros are pushed into the stack, and when the ones occur, we try to pop them out. So that is how the push down automata actually works. Now in Turing machine, there is no memory element like a stack to store the elements. But here what we do is, we need to check each zero. For example, if the string is 000111, so for each zero, we'll be checking 1 and come back to the next 0. So there is a chance of the reader head moving both sides, that is left or right. So the finite control can move from the first 0 to the next first one and come back to the second 0 and check the second one, and so on. And to identify how many zeros we have already checked, we require the tape symbol, so we can mark on the tape so how many zeros we checked. So the transition table can be written as follows. So let Q naught be the initial state here, and this 0 and 1 are the input symbols, this is sigma, and x and y let them be the tape symbols, and capital B is the blank space. So why do we use x and y here is to mark the zeros and ones. So here I am taking x as the symbol to mark the zeros which are already been processed, and y is for the ones which are already been processed. So now in the first state, initially the string always starts with 0 because the first symbol always in this language is 0. So what is the process? We mark this 0 as x and we proceed to check for a 1, the availability of a 1. So here what we write this transition is when q not on 0, what we do is we mark that 0 as x and we move right side. So this is the indication q1 xr that indicates we go into the next state q1 and we mark that 0 as x and we go to the right hand side. So first 0, that is, if this is the string, it marks this 0 as x and it goes on checking. So in this next state we get a 0, that is in q1 state we get a 0, but we are interested in finding a 1 in q1 state. So in q1 state what we do is we don't change the state, or else we don't change the symbol, we just keep on ignoring all the zeros until we reach a 1. So at the point somewhere we, after all zeros are been left in the q1 state, we reach a symbol called 1. So in that state, generally again change that 1 as 1 and come back to the left side, checking for the second one. So we'll come back again. So again this time we changed the state as q2. And in q2 state, we're not going to change any symbol, just we are going to the start of the string where we have left that zeros. So here no matter how many zeros are there, we ignore all of them until an x is reached. So when the x is reached, we consider that that is the start of the symbol, or is the where we already have processed the number of zeros. So once this is reached, we already go to the initial state again and we start again the process from the first. So here clearly Q0 is making zeros into x and Q1 is interested in making 1 as y, and Q2 is a dummy state where we just go to the initial state or else initial position where we have left the zeros. So here we fill the remaining blocks in the table, the remaining columns in the table. So at Q1 at y, Q1, this is the state Q1 by this one. So here what we write is, so even if there is a y, we simply ignore that because we are interested in finding for a 1. So simply ignore that. So we can write q1 y and right side again. And finally, this is done successfully and at q2 at y, because once some ones are processed, it will come back immediately. It will find a y here. So after, for example, if these two are made 1 in q2 state, it will come back with a state called y here with an input symbol. So even in this, q2 state is only interested in going to the first possibility, that is finding the zeros. So again it will go to left side and so on. And if it is done successfully, that is, if all the zeros are made into x and all ones are made into y, at the end you will find the blank space, which is true for every string in the Turing machine. So here, after all zeros are made into x and it will, after making this last one as y, it will come back checking for any other zeros left. And if there are no zeros left, immediately in q0 state we find a symbol called y, which indicates that all these zeros are been processed already. So there should not be any number of ones. So simply in q3 at y, q0 at y, we go to some new state called q3, leave that y as it is. And in q3 state, there shouldn't be any zeros or ones left out. So we don't write any transition here. Only we try to ignore all the y's and find a blank space. So in q3, all the y's are ignored. And if it find a blank space at the end, you can go to a final state. So let it be q4 here. So assume that q4 is the final state here. So all the remaining transitions are not existing here. There won't be any meaning for that. So this is how we design a Turing machine using the tape symbols for accepting the language 0 power n, 1 power n. For example, if this is the language is same language, or else the machine is given for the language, some language 0 power n, 1 power n and 2 power n. Here also we follow the same logic, that is just mark the 0 as x, check for the 1 and mark it as Y, check for the 2 and mark it as Z, and come back to the initial position checking for the zeros, the availability of zeros. So for each zero, check the availability of 1 and the availability of 2. Since there is no memory element like a stack available here where we had that for a push down automata, here we simply check for the symbols, and using the state symbols we can mark on the tape so that we can recognize how many number of symbols are already being processed. So diagrammatic representation of this table can be shown here. So the initial state Q naught, here this is the Q naught, this is the initial state. Q naught on 0, we are going to Q1 state, and that 0 is replaced as X, and we are moving it right side. And here that first 0 is marked as X and going to the next state. And here in Q1, we are not bothered about zeros, so we ignore all zeros by moving that right side. And when a 1 is found, we are making it as 1, right, and coming back to the left side. So in Q2, we just waste the symbols zeros and until we get that X. So finally, when we get X, we come back to Q0 state. So the cycle repeats, the same cycle actually repeats here until all the zeros are finished. And once all the zeros are finished, Q0 gets only Y. So we won't get any one symbol 1 in Q0 state. And finally, if all the Y's are equally processed, then in Q3 state, there is a blank space available, then we go with the final state Q4. So this is how we represent the same table as a transition diagram. So this is the construction of a Turing machine. We'll see different examples in the next class. Thank you all.